So in today's Meow seminar, we'll have the pleasure of listening to Girish, who will tell us about Fourier growth of XOR-fibers of communication protocols. So please, Uma, take it away.
Thank you. So I'll be talking about Fourier growth of XOR-fibers of communication protocols. This is based on a joint work with Makran Sinha, Avishai et al, and Kevin Wu. This will be a fairly short and informal talk, so please feel free to interrupt me with questions. Okay, so let's get started. I'll start by telling you about all the concepts in this title of this talk. So let's first start with Fourier growth. So broadly, we're talking about Fourier analysis, which involves the use of analytic techniques to study functions on the Boolean hypercube, the space of functions on -1 to the power n. This is a very important field and has applications to many areas, including learning theory, social choice theory, hardness of approximation, random graphs, property testing, and so on. The main object of study here is functions on the Boolean hypercube. The set of all real-valued functions on the Boolean hypercube forms a vector space with a very natural inner product given by the correlation. So the inner product between two functions f and g is the correlation between f and g under the uniform distribution on the hypercube. There's a very natural orthonormal basis for this family of functions given by the parity functions. So for every subset of n, you have a parity function xs, which computes the parity of coordinates in S. This corresponds to the parity in the -1 world, where you take the product of coordinates in S. This forms a very important orthonormal basis for the family of all Boolean functions. And finally, we can talk about Fourier coefficients, which are going to come up a lot during this talk. Given a Boolean function, the Fourier coefficients are basically the projections of the function onto the various parity functions. In particular, f hat s computes the correlation between f and the parity function on S. So these various parity functions measure how much f looks like the various parity functions. We're finally ready to define the main Fourier analytic object of interest, which is Fourier growth. Fourier growth refers to upper bounds on this quantity called the level L mass. Given a Boolean function, the level L mass is the sum of absolute values of Fourier coefficients of sets of size L. So it is summation mod of f hat s, where s is of size L. In other words, if you look at the vector that is composed of all the level L Fourier coefficients, this quantity computes the L1 norm of that vector. So this is going to be the main Fourier analytic quantity of interest. In the next slide, I'll try to give you some intuition on what this level L mass tries to capture. But for now, are there any questions on the definitions? Okay, so let me now give some intuition as to what this level L mass tries to capture. So loosely speaking, the level L mass kind of computes how well the function is at detecting weak signals in the input. In particular, if you look at level 1 mass, it captures the ability of the Boolean function to distinguish biased coins from unbiased coins. So in more detail, the majority function is an example of a function that has very large Fourier growth. Its level 1 Fourier growth is roughly square root n, which is about as large as it can be for bounded Boolean functions. And this function can distinguish inputs which are slightly biased towards 1 versus slightly biased towards -1. What I mean by this is that if you draw each coordinate independently with expectation 1 over square root n, the majority function will be highly biased towards 1. Whereas if you draw it IID with expectation -1 over square root n, the majority will be biased towards -1. In this sense, the majority is an example of a function that can detect a bias of 1 over square root n, and accordingly, its level 1 Fourier growth is large, roughly square root n. It turns out that functions with small Fourier growth cannot detect small biases. So this is the statement of the coin theorem. The coin problem in general studies what is the maximum advantage with which functions can differentiate delta bias from minus delta bias, or equivalently delta bias from unbiased. And the Coin theorem says that this maximum advantage for many natural family of functions is essentially captured by the level 1 mass. So the ability to detect bias delta, the advantage is at most delta times the level 1 mass. In particular, any family of functions that can detect delta biased must have large level 1 Fourier growth, at least 1 over delta. This is one of multiple phenomena that Fourier growth tries to capture. So there are a lot of
Question
applications.
at this point.
Yes.
So is it, I mean, we're using the L1 norm. Is this important? I mean, what if I don't know, use the L2 norm or whatever, looking at the same quantity, or is it like L1 is particularly good for this?
Yeah, there's something slightly different about L1 norm and L2 norm. So for example, you can show that actually a random function will have very small L1 norm. Whereas, yeah, so yeah, there are some ways in which, so for example, if you look at a completely random function, its level 1 norm will be something like 2 to the minus n, whereas for majority it is square root n. So in some sense, it's slightly different from the typical measures, which are usually large for random functions.
Mm-hmm. Okay.
If that makes sense.
Thanks.
Yeah.
Yeah. Mm-hmm.
Yeah, it's very much a measure of how well the function can aggregate weak signals in the input. Yeah.
Makes sense. Thank you.
Mm-hmm. Yeah. Yeah, so apart from this level 1 Fourier growth, there are many applications of Fourier growth for higher levels. So the original motivation for studying Fourier growth was learning theory, where essentially it was shown that functions with small total Fourier growth are easy to learn in some sense. In the field of quantum versus classical separations, it turns out that Fourier growth is the key concept that separates quantum from classical. It turns out that quantum algorithms can compute some functions with large Fourier growth, for example, the correlation function. But on the other hand, classical models cannot compute any function with a large Fourier growth in some sense. And finally, Fourier growth also has applications to the field of pseudorandom generators. And it turns out that functions with small Fourier growth are easy to fool. You can construct simple and efficient explicit pseudorandom generators if you have bounds on the Fourier growth.
And is it again, you gave us the intuition before that somehow if you have high, if this measure is high, then you're good at picking up weak signals. So you could be somehow brittle, but if functions have small measure, then they're easy to learn because they're somehow fairly robust. They can't be too complicated. Is that how I should think about it? And similarly, like if I'm trying to fool an algorithm, the pseudorandom generator, then somehow the algorithm has to be pretty delicate to detect the pseudorandomness, and it can't be if it has.
Exactly. Yeah.
Okay. Thank you.
Yeah. Yeah. Somehow, if you look at just level 1 coefficients, you can mimic the completely uniform distribution by this distribution where each coordinate has bias delta. So that already says that, you can mimic the uniform distribution by this slightly biased distribution for the level 1 case, but the higher levels also you can control by using higher level Fourier growth bounds. So it's quite complicated, the construction of the pseudorandom generator, but yeah, intuitively that's the idea. Yeah. Yeah, so these are the applications of Fourier growth bounds. And these kind of bounds have been studied for many different models of computation. I've listed some of them in this slide. And the one I want to highlight is the class of low degree polynomials. So degree D polynomials over F2. So the reason I wanted to highlight this model is because it really shows how hard proving Fourier growth bounds is. For this model, we know that the level 1 bound is at most polynomial in D. If you could prove the same thing for the level 2, then it would imply simple and explicit pseudorandom generators for AC0 circuits with parity gates. This is a major open question, and it would follow if you could prove a level 2 bound of polynomial in D. So this model really highlights the difficulty of proving Fourier growth bounds, even for the first few levels. Another two models that I want to talk about are decision trees and parity decision trees. These are some simple kinds of computational models that come up in the field of query complexity. And they've been very well studied, but interestingly, their Fourier growth was only understood recently. So now we know that for depth D decision trees, the level L mass is like square root D to the L. And this is optimal, essentially. I'm ignoring some polylog n factors here. The optimal, this bound is optimal in terms of D. So this is the situation for decision trees and parity decision trees. And what we will study in this talk are what is called XOR-fibers of cost D communication protocols. I'll define this later, but it turns out to be a more general family of functions than depth D decision trees and parity decision trees. So in some sense, it generalizes these two models. And we'll be interested in studying Fourier growth for such objects. So in the next few slides, I'll tell you a little bit about communication protocols. I realize that many people here are an expert in this topic, but please bear with me. I'll be talking about a communication complexity first. And this is basically the field that studies the amount of communication needed to compute functions with distributed inputs. In particular, you have a function f that depends on x and y, two n-bit inputs, and Alice gets x, Bob gets y, and they want to evaluate f of xy while minimizing the amount of communication between them. The communication typically proceeds in rounds, and in each round, we'll assume that Alice or Bob sends a single bit to the other player. This message that they send can be a function of their own input, as well as the history up to this point. So this communication is inherently adaptive. And finally, we'll have Alice announce the answer. So this is the standard deterministic model. We will also talk about randomized models where the players may share randomness and they're allowed to make errors with probability at most 1/3. Typically, during this talk, we'll only focus on deterministic models, but some of our results will just generalize to randomized models. So in that case, I'll mention it. But for now, just think of deterministic protocols. We measure the cost of a communication protocol by the total communication that they exchange. So this is the description of the communication complexity model. And the study of this has applications to several areas in TCS, which I've listed here. So let me start by giving an example of a communication protocol. The way we are going to view communication protocols is using a tree-like structure. This tree informs the players what message they need to send on a given input and given the history. So in this protocol, Alice first starts by announcing the value of x1. And since x1 is 1, Bob proceeds to announce the value of y1. Since y1 is -1, Alice proceeds to announce x2, and then Bob announces y2, and finally Alice can output the label of the leaf, which is 1. This is called the output of the protocol. So this is one simple example of a communication protocol of cost 4. And the function computed by this protocol is some simple function that depends on just 4 coordinates of the input. This is an example of a very structured communication protocol that corresponds to a decision tree in query complexity. I've not told you about query complexity, but briefly it studies how many coordinates of an input need to be read in order to compute a function. Given a function f from -1, 1 to the n, how many queries are needed to compute f of x? How many times do you need to read the coordinates of x? So this is what query complexity tries to capture. And as you can see here, this communication protocol has the kind of structure where you're reading a coordinate one by one. In general, communication protocols can be more complicated. So for example, you can take protocols where the players are allowed to reveal parities of subsets of coordinates. This is slightly more general, and it corresponds to what is called a parity decision tree in query complexity. This is a model where you can query the parity of any subset of coordinates. In full generality, communication protocols can communicate arbitrary functions. So, for example, Alice can announce f of x for any binary function f. Similarly, Bob can announce g of y for any binary function g. These functions f and g are public knowledge, and they can be chosen adaptively. The only unknown here is the other player's input. So this is how general communication protocols look like. And this kind of freedom allows communication protocols to be very expressive. So for example, the players can compute any function that depends only on x using zero communication. This is because Alice can just evaluate the function entirely by herself and announce the answer. So this makes communication complexity lower bounds harder to argue than, say, decision tree or parity decision tree lower bounds. So now I want to talk about a special class of communication complexity problems known as XOR problems. But maybe I can take questions now if there are any.
Yes, so far, so good. Just curious, you mentioned that some of your results will generalize to even randomized communication complexity. Would there be any way you could capture also rounds, or is this like you're oblivious to how much sort of interactivity there is between Alice and Bob?
Oh, that's a great question, actually. I would think that your Fourier growth behaves slightly differently. Like it increases the more number of rounds you have, and the bound we have is oblivious to the number of rounds, though. Although I think it's possible that Fourier growth might capture more sensitive phenomenon. In the query complexity world, you can actually show some kind of hierarchy of Fourier growths based on the number of rounds of queries you make. So it's possible that, it's possible that Fourier growth for communication protocols can capture the number of rounds. But in our work, we only care about the total cost.
Okay, interesting. Thanks.
Yeah. Okay, so now let me talk about XOR functions. These are a special class of problems in communication complexity, which have applications to the log-rank conjecture, approximate log-rank conjecture, and quantum versus classical separations. So here, the function that Alice and Bob wish to compute depends only on the XOR of x and y. So in particular, given a Boolean function on n bit inputs, you can define the XOR lift of f, which is a communication problem, where Alice gets x, Bob gets y, and they wish to compute f evaluated on x XOR y. In this problem, the output of the protocol, the output of the function they wish to compute, depends only on the fiber x XOR y in some sense. So these are known as XOR problems, and they're a very important class of problems in communication complexity and have connections with lifting theorems and so on. Let me just mention that you can lift other functions as well. So this is a more general phenomena. Given any gadget, you can define a communication problem called the G lift of f. Essentially, the players first need to apply G on all the n blocks and then evaluate f on the output of all the n blocks. So earlier we looked at XOR lift, where this gadget is just the XOR, but you could consider lifting with more general gadgets, and this is very well studied. Another gadget that people care a lot about is the inner product gadget and also the indexing gadget. It's not too important what exactly these gadgets are, but what's interesting is that they can be used to show lifting theorems. So what are lifting theorems? Lifting theorems allow you to translate query complexity lower bounds to communication complexity lower bounds. Lifting theorems typically show that if you have a query complexity lower bound for some function f, then it pretty much gives you the same communication complexity lower bound for the G lift of F, which is a communication problem. These kind of lifting theorems are very well studied and have a lot of applications. Of course, in this talk, we're going to be interested in lifting with XOR gadget, and sometimes we'll be talking about constant size gadgets. So we'll be interested in XOR lifts. Okay, so now that I've defined the XOR lift, I can define the XOR fiber, which is in some sense the opposite of an XOR lift. So here you're given a communication protocol and you're going to define a Boolean function as follows. Take all inputs of the form x, x XOR z and take the average output of the protocol over all such inputs as you vary x. This gives you a function of z, and this is called the XOR fiber. So pictorially, this is how I depict it as a picture. And what's happening here is that you're taking all points x, y, whose XOR is fixed, say z, and you're taking the average output of the protocol over all such inputs. This is a function of z, and we're calling this function the XOR fiber. This XOR fiber is in some sense the opposite of an XOR lift, in the sense that if you have a protocol that exactly computes the XOR lift of a function f, then the XOR fiber of the protocol is precisely the function f. So this is what an XOR fiber does. And although this term has not explicitly appeared in literature before, it's been implicitly studied in the field of XOR lifting. So now I'm ready to finally explain all the words in our title. Basically, we study Fourier growth bounds for XOR fibers of communication protocols. We try to show optimal Fourier growth bounds as a function of the cost of the protocol. So this is the problem that we study. In the next slide, I'll give some motivations for studying this XOR fibers of communication protocols, but let me take questions now.
Yeah, so I'm trying to understand this XOR fiber. So it's sort of, I mean, if this would be somehow a quantity that is very related to, suppose I wanted to prove like a lifting theorem for just binary XOR gadget, and this should be a well-behaved quantity, or how should I think of it?
Yeah, in some sense, if you're exactly computing if you have a lifting theorem for, say, deterministic protocols, then the XOR fiber would give you back the original function that you're trying to compute.
Yeah, but in some sense also, like in some sense, morally speaking, unless the protocol is doing something really crazy, then in some sense this expectation shouldn't, I mean, the dependence on the protocol in some sense should probably only be on Z, right? The protocol should not depend so much on X in this definition of yours in some sense.
Yeah, so this kind of averages out X. So
yeah.
So this does average out X, and hopefully the idea is that it becomes a highly simplified object. So even though communication protocols can be complex, somehow you want to say that this averaged out object looks like a decision tree of small cost or something like that.
Yeah, but this average object somehow, morally speaking, should be close to the actual thing, in the sense that because if you're computing this XOR, you're really only interested in Z. Like, you shouldn't behave very differently depending on whether Alice has X1 or X2. It's somehow the XOR of Alice and Bob is only what should influence the protocol in some sense.
Right, that's true. That's true.
Okay. Although, I mean, proving it is a completely different matter, of course, but
yeah,
yes,
so
okay.
Yeah, ideally, these objects themselves should be approximable by parity decision trees, but we just show that when it comes to Fourier growth, they behave like parity decision trees, if that makes sense.
Makes total sense. Thank you.
Yeah. 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 So now let me talk about some motivations for studying this concept. And yeah, as you can imagine, lifting kind of comes into the picture here. So yeah, so one connection is to lifting theorems for constant size gadgets. So this is a major open question, to get a perfect lifting theorem for some gadget that is on constantly many bits. And any such theorem, it turns out, would imply Fourier growth bounds for XOR fibers. Essentially, the idea is that when you look at constant size gadgets and when you look at Fourier growth, it's all equivalent in the sense that if you can prove Fourier growth bounds for some constant size gadget, it kind of follows for all gadgets. So in particular, it would imply Fourier growth for XOR fibers. So maybe before we try to prove optimal lifting theorems, we might want to prove optimal Fourier growth bounds. So in particular, before you prove lifting theorems for XOR gadget, you would first need to show optimal lifting theorems. You would first need to show optimal Fourier growth for XOR fibers. So this is one connection. And now I'll focus on the applications of Fourier growth bounds for XOR fibers. And the first application is what I described earlier, which is the application to parity decision trees and standard decision trees. So you can show that XOR fibers are a generalization of decision trees and parity decision trees in the sense that given any depth D decision tree, you can produce a communication protocol of cost 2D whose XOR fiber is precisely that decision tree. Therefore, any Fourier bounds you prove for communication protocols immediately hold for decision trees and parity decision trees. And for these models, even though these models themselves are very well studied, only recently we discovered the optimal Fourier growth bounds. For depth D trees, it turns out to be square root D to the L, and this dependence on D is optimal. And if you could show such a bound for XOR fibers, then it would subsume all these bounds in this slide. So this is one application of Fourier growth of XOR fibers. The second application, which was actually the motivation for us to study this, was the field of quantum versus classical separations. Let me tell you the history of quantum versus classical separations in query complexity. The strongest separation we have is due to this function called k-fold correlation. This is a function whose quantum query complexity is k over 2, but the randomized query complexity is n to the 1 minus 1 over k. Furthermore, this is an optimal separation in the sense that any quantum algorithm with these many queries can be classically simulated with these many queries. And interestingly, the measure that was used to separate these two quantities was the level k Fourier growth in some sense. So we have this optimal separation in query complexity, and we ask, what is the best separation we have in communication complexity? As I hinted at earlier, one way to get such a separation is to use lifting theorems. In particular, if you take the lift of the correlation function with the inner product gadget, you get a similar separation between quantum communication complexity and classical communication complexity, where the quantum protocol uses k rounds. And the question we ask is this optimal? Is this the best possible quantitative separation between quantum communication complexity and classical communication complexity? We suspect that this is not the optimal separation. In particular, because we are using an inner product gadget, which is significantly more complicated than the XOR gadget, the quantum protocol seems to require twice as many rounds as you would expect. So we believe that lifting with a simpler gadget, such as the XOR gadget, would reduce the number of rounds required. And indeed, this turns out to be true. You can show that if you lift it with the XOR gadget, the quantum protocol requires only half as many rounds as before. But now the question is, can you prove the classical lower bound? We don't have lifting theorems for XOR gadget, but can we hands-on show that for this problem, the classical communication complexity is at least this much? In order to prove this bound, we really need to understand Fourier growth bounds on XOR fibers. If you could prove the optimal level k bound in some sense, you would get this lower bound of n to the 1 minus 1 over k. And we suspect that this is an optimal separation between quantum and classical in communication. Okay, so finally, I want to talk about the application to the gap hamming problem. The gap hamming problem is an important problem in communication complexity, and it has applications to streaming lower bounds. In this problem, Alice gets X, Bob gets Y, and they want to tell whether the X XOR Y has large Hamming weight or small Hamming weight, where this large and small differ by like square root n. So in other words, they want to distinguish between the coordinates of X XOR Y being slightly biased towards 1 versus slightly biased towards -1, where this slight is like 1 over square root n. So this problem requires communication complexity omega n in the randomized model. And there are many different proofs of this. And as you might have guessed from the coin problems that we talked about earlier, another way to prove this lower bound is using Fourier growth. So let me describe that in more detail. So recall the coin theorem, which says that the maximum advantage in distinguishing delta bias from minus delta bias is proportional to the level 1 Fourier growth. It is at most delta times the level 1 mass. Now, I claim that if you can show Fourier growth on XOR-fibers, then you get a lower bound on the gap hamming problem. So in more detail, suppose you have a protocol that solves the gap hamming problem. This means that the communication protocol can distinguish inputs whose XOR has bias 1 over square root n versus the XOR has bias -1 over square root n. This implies that the XOR fiber of the protocol can distinguish inputs where each coordinate has bias 1 over square root n versus -1 over square root n. By the coin theorem, this implies that the XOR fiber must have large level 1 Fourier growth. It must be at least square root n. Now, if you could show an upper bound on the Fourier growth in terms of the cost of the protocol, then it would give you a lower bound on the cost of the protocol, the cost of any protocol that solves the gap hamming problem. So this is another application of Fourier growth for XOR fibers.
So just to clarify, is this, are we deterministic here, or this would work in a randomized setting? Or?
That's a good point. So actually, I should have mentioned this earlier, but so if you can prove a Fourier growth bound on XOR fibers of deterministic protocols, it just immediately implies Fourier growth for randomized protocols, simply by convexity. If you have a family of functions that has Fourier growth, then the average of them will also have bounded Fourier growth.
Okay, thank you.
Yeah. Yeah, so once you can prove Fourier growth for deterministic protocols, it follows straightforward for randomized protocols. Okay. Okay, so now I'm ready to talk about our main result. So we study the best possible Fourier growth bounds for XOR fibers. The hope is that for protocols of cost D, in terms of Fourier growth, they behave just like decision trees of depth D. So the hope is that the level L mass is at most square root D to the L, which is what you would get if you had a decision tree of depth D. The best bound we had before was D to the L. And in our work, we bridge this gap between D to the L and square root D to the L. We prove an optimal level 1 bound of square root D. There are no polylog n factors here. For level 2, we improve the bound from D squared to D to the 1.5 with some polylog n factors. We suspect that the correct bound is actually D times polylog n factors. So this is our main result. We give a few applications of this. The first is using our level 1 bound. We give a new proof that the gap hamming problem requires omega n randomized communication. We use our level 2 bounds to improve the best communication lower bounds for the correlation problem from n to the 1/4 to n to the 1/3. We suspect that the correct answer is n to the 1/2, and that's optimal if you could show the correct level 2 bound. Finally, our level 1 bound gives a new proof of the optimal Fourier growth bounds for decision trees and parity decision trees. So this is our main result. In the next few minutes, I'll talk about the proof overview, but now is a good point to take questions if there are any.
So one thing, let's see if this question even makes sense. So suppose I have a problem where I suspect, like, I do an XOR lift and I suspect the deterministic communication complexity might be fairly high, but not necessarily the randomized one. So then maybe, is this a kind of lower bound that I would expect then XOR-fibers not to pick up because they sort of don't, I mean, they immediately apply to the stronger setting?
Yeah, Fourier growth probably cannot distinguish between decision tree, deterministic and randomized.
Okay.
Yeah, yeah.
Makes sense. Thanks.
Mhm.
Can I ask a question which is probably not so easy to answer? This square root that appears everywhere, is there an intuitive reason why it does so? Or is it, like, can you say, is there a short explanation of why you would expect something like that?
Yeah, maybe let me try to give a short explanation. So let's look at a simple decision tree where you're just revealing the first d coordinates. And let me try to convince you that the level 1 bound is square root d as opposed to d. So basically the level 1 bound, you're adding up all the level 1 Fourier coefficients. Forget about the signs for now. We're just looking at the sum of level 1 Fourier coefficients. Now let's just look at a leaf. What is the level 1 Fourier growth for a leaf? It's just the sum of the coordinates. So in a leaf, you're going to set some coordinates to 1, some coordinates to -1, and the rest to 0. And I claim that the Fourier coefficients of this leaf are precisely given by the values to which you set So for example, if from a root to leaf, I set the first t coordinates to some bit string a consisting of ±1, then the Fourier growth of the leaf is precisely the sum of ai. So the idea is that when you walk down a decision tree, with probability half, you're going to set the coordinate to 1. With probability half, you're going to set the coordinate to -1. So each time you're doing this, it's like you're adding a random bit to the Fourier growth. So after d steps, in the worst case, you could have set all the d coordinates to be 1, in which case your Fourier growth would be d. But typically, you would set half of them to 1 and half of them to -1. And when you add them up, you would get something like square root d.
Okay.
Yeah. So I think we'll see this example a little more explicitly in a few slides. After a few slides. But that's the kind of idea. The d becomes square root d because of cancellations that occur when you go down a tree.
Right. Okay. Thanks.
Yeah. Okay. So any other questions? Okay. So let me give a proof overview. Okay. Yeah. So the proof consists of 3 steps. In the first step, we're going to express the Fourier growth as a martingale on this protocol tree. So first, you can view the communication protocol as a tree. We're going to sample the inputs to Alice and Bob uniformly and independently. and this induces a random walk down the tree. We're going to express the Fourier growth as a martingale with respect to this random walk. In particular, it will turn out that the Fourier growth, level L Fourier growth, is bounded by the expected modulus of the martingale at a random leaf. So you need to bound the expected modulus of a certain martingale. In other words, it suffices to bound the expected square of the martingale at a leaf. And to do this, you need to bound the sum of squares of step sizes of the martingale. It turns out this is difficult to do for general protocols. So in step 2, we introduce some simplifying assumptions on the structure of the protocol. And under these structural assumptions, we prove the bound on the sum of squares of step sizes. In step 3, we justify this assumption. We show that you can take any protocol and convert it into a protocol with this structure without blowing up the communication cost by much. This uses some kind of density increment or structure versus pseudorandomness argument. The key notion of structure turns out to be some kind of almost k-wise independence. So this is the broad framework. So it turns out that for parity decision trees and decision trees, you can prove optimal Fourier growth bounds using exactly this framework, but you can use perfect k-wise independence. This is because parity decision trees and decision trees are so structured that you can enforce perfect independence on the intermediate sets. But for communication protocols, this turns out to be much, much more complicated. So the reason is that because communication protocols are so expressive, the sets that Alice and Bob have throughout the protocol are just arbitrary subsets of the Boolean hypercube. So it's going to be impossible to enforce perfect k-wise independence. So we can only enforce some approximate notion of k-wise independence. And a priori, it's not even clear what the correct notion should be that would allow you to prove Fourier growth. That is one of the key contributions in our work. We identify the right notion of k-wise independence, almost k-wise independence, that allows you to control the Fourier growth. The second difficulty is in the cleanup process, where we convert arbitrary protocols into structured protocols. This turns out to be very technically involved, and this is the reason why we're not able to prove the optimal level 2 bound. So yeah, these are some of the issues that come up when we try to execute this proof.
When you describe it, here's another vague question, I'm afraid. So when you describe the proof in this way, it sounds a little bit like, I mean, suppose I wanted to do a lifting proof, I would somehow, look at the communication protocol and I would start descending in it and then clean up the rectangles as I go to maintain some kind of structural properties. Is it in some sense, something similar, or is this just completely, utterly unrelated? I don't know if the question has a well-defined answer, but.
No, that's a very good observation. And indeed, it has a very similar flavor. Like so there you use some kind of blockwise density or some different notions of having enough entropy. And here it does, the framework is very similar. But the notion of k-wise independence that we use seems different from what people have usually studied in lifting theorems. So I would say the broad outline as such looks very similar. You go down a tree and you do this kind of structure versus pseudo-randomness type argument. But the exact measure that we keep track of is slightly different, I would say. It's not blockwise density or things like that.
Okay, thank you.
Yeah. Yeah, so maybe in the next few slides, I'll tell you what notion of structure we use. I'll not explain how you can use it to prove Fourier growth bounds, but instead I'll focus on step 3, which is the technical part, and tell you how we handle that. Okay, so first, let me introduce the notion of independence that we use, and I'll specifically focus on two-wise independence. So this is the notion of almost two-wise independence that we use. It is a spectral notion. So given a set, we say that it is elongated in direction B, if the variance of the set in direction V is large. In other words, you sample a random point from S, and you look at this random variable, the inner product between X and V. If this random variable has large variance, we say that a set is elongated in direction V. We say that a set is spectrally two-wise independent if it is not elongated in any direction. You can depict it as shown in this slide. There's another way of defining spectral two-wise independence, which is you look at a random point sampled from S and you look at the covariance matrix corresponding to X. If this covariance matrix has bounded spectral norm, then S is spectrally two-wise independent, and vice versa. So this is some kind of spectral notion of almost two-wise independence, and this is the key property that we use to control the Fourier growth. We want Alice's and Bob's sets to satisfy this property throughout the protocol, or at least at certain key nodes in the protocol. It turns out that using this, you can prove Fourier growth bounds. Maybe in the next few minutes, I'll describe how we guarantee the spectral two-wise independence. How do we clean up a protocol to ensure this property? But any questions about the definition of spectral two-wise independence? Okay. So yeah. So let me describe how we clean up a protocol to guarantee spectral two-wise independence. The cleanup process is very natural. Given a set that is elongated in some direction, we partition it into slices perpendicular to the direction. So we partition the set based on the inner product with this bad vector V. The point of doing this is to reduce the direction along, reduce the variance along direction V. So if you look at any particular slice, the variance in this direction V is 0. So this is a slightly weird step in which I'm partitioning it based on partitioning a discrete set into continuous things. So there are some things that need to be done. So either you could assume that each slice is, slightly thick in the sense that you announce this, you partition the set based on the approximate value of this inner product, or you can allow real inputs and real outputs, and basically your inputs also come from a continuous space and so on. Yeah, there are pros and cons to doing either, but I'm not going to go into that now. Let's just imagine that they're revealing this up to infinite precision. Now the question becomes, how many times do you have to do this? The main technical lemma for level 1 is that this process can be done with not too much blow up. In particular, if you have a communication protocol of cost D, the cleanup process, you can produce a new protocol where basically all the nodes are clean, but your depth is only order D. So just to give you a special case of this lemma, we obtain a result that was earlier shown by Tomavidic. So this result says that if you have a set that is not too small, there cannot be too many directions along which the set is elongated. In particular, if you have a set of measure e to the minus t, there can be at most d bad directions for this set. The intuition behind this is that whenever you have a set that is elongated along some direction, that direction gives you one bit of information about that set. And because your set is of measure e to the minus t, you cannot have more than d bits of information about this set, which means that you can have only d directions along which the set is elongated. This is the idea behind the special case of the lemma, but let me just say some of the difficulties that come up when proving the main lemma. The main lemma turns out to be much more complicated because for us, it's not enough to just clean the leaves of the protocol. We somehow need to clean all the rectangles during the protocol. And this makes the cleanup process inherently adaptive. So first Alice is going to partition her set, and then we're going to clean the protocol. Then again, she's going to partition her set and so on. So we need a way of doing this lemma adaptively as you are partitioning the space. Secondly, the cleanup process itself is kind of adaptive. If you have a set that is elongated in some direction and you start cleaning it up, it could produce new bad directions. So we need a way to handle these adaptive cleanup steps. So this makes the main lemma significantly more complicated, and we have to use some potential function arguments and so on. But this is the main idea behind the level 1. Let me conclude by just stating the problem for level 2, which is kind of easy to state, without the context of communication complexity, but this is the main problem that we care about. So here we want to make sets 4-wise independent. So what do I mean by 4-wise independent? You look at this random variable, which is inner product between X tensor X and V. So earlier we looked at inner product between X and V, where V is an n-dimensional vector. We looked at linear forms, but now we're going to look at bilinear forms. We're going to look at the inner product between X tensor X and V, where V is an n-square length vector. And we want the variance of this random variable to be small. So we say that S is spectrally 4-wise independent if it is not elongated in any bilinear form. The main open problem here is to show a way of partitioning an arbitrary set into few parts where each part is spectrally 4-wise independent. In particular, given a set of measure e to the minus t, can you partition it into 2 to the order d parts such that typically each part is a spectrally 4-wise independent? So this is the crux of the problem for level L equals 2, and this is still open. So yeah, this is all that I wanted to say about the proof.
And is there anything you can say? I mean, because you did get something for level 2, right? But is it at all related to this, or this is like by other means?
Yeah, this is exactly the problem we solve. So the way we handle this is, instead of saying spectrally, so basically what we do is, basically we relax the notion of what it means to be elongated. So we change this quantity 10 here to square root d. And then it turns out that you can partition it into 2 to the d parts. But then you're allowing a larger variance, so the bound you get is also slightly larger. Yeah, so basically, this is, it's the same framework. It's just that we change the definition of elongatedness so that we can prove a bound. Yeah.
Okay, but you say, so here 10 wasn't like, I guess it's an arbitrary constant, but it's really constant, but then it turns out you can play with it between like square root d and 10, I guess, but.
Exactly. Yeah, it just turns out that so the new protocol should have cost order d, and the only setting of parameters under which we were able to prove it is to set the 10 to be square root d. But it could potentially hold even, there might be another argument which says you can clean up with just 10. Yeah.
Could you also get a worse bound by having the 10 and then partitioning in more parts so the protocol would increase, or would that not work?
Yeah, that's a good point. So it seemed to be that if you just keep 10, then the depth blows from d to d square. And if you blow the depth from d to d square, then the previous bound itself gives you you shouldn't blow by more than a quadratic factor. You have that, you have that condition.
Yeah, that makes sense. Thanks.
Yeah. Yeah. So yeah, if there are no other questions, then yeah, this brings me to the end of my talk.
Okay, so thank you so much. So clapping on behalf of the audience virtually. I guess we had a bunch of questions during the talk already. I think everybody should feel free to just insert any additional questions. So do you want to say anything about this? Because you mentioned also a martingale argument in some other part of the proof. Do you want to say anything about this part?
Yeah, actually, I wasn't sure, like, so I was told that there's going to be another session here. I guess I could tell you more about it, but maybe you want me to say something short about it. So
we'd be super excited to hear more if you're willing to continue after the break, definitely. But yeah, maybe something, brief, maybe. Yeah, so another question would like, if we continue with the technical part, like what would you say? What would you see more?
Yeah, so I guess, yeah, there are many things we could focus on, like, I accidentally closed it, so yeah, so yeah, there are, I guess, many things we could see. Like the first one is how do you even write down this martingale? The second step is why is spectral two-wise independence the correct thing to do? And the third step is this cleanup process. I guess I don't have much to say about the cleanup process because it's somewhat technical. So if we focus on something, it would either be the first or the second part. Yeah, the first part really gives you the description of this martingale, at which point it kind of becomes clear why this Fourier growth is a martingale. But if I had to say just like a few lines about it, I would say it kind of captures the phenomenon that I hinted at earlier. When you go down a decision tree, the Fourier growth has this martingale-like structure. It's as though you're adding d random coins, each of which is plus minus 1. And it turns out that in the communication complexity world, you also have a martingale, but it's no longer as simple as adding a random coin at each step. It's a more complicated martingale where what you add at each step depends on the cleanliness of the protocol. In the sense that if your sets are k-wise independent, then it's like you're adding a random coin at each step, very loosely speaking.
I see. Yeah, so maybe we should return to it after the break. Just another vague question, but I was thinking about, so far it seems that we looked at XOR-fibers of functions. Like suppose, I mean, another, if you look at lifting theorems in communication complexity, one interesting thing is that the lifting is so strong that it automatically works also for relations, right? Because you're just hiding to what extent Alice and Bob can sort of compute the reveal information about the coordinates. Whereas for XOR-fibers, it seems we wanted to look at at least the way it was defined, like you need a function that you're computing. Do you see that, or is there any way that I could extend this to relational problems?
Yeah, that's a good question. The biggest hurdle I see is, I think, more than the fact that there are many outputs, is the fact that you have this thing called Fourier growth, which kind of only gives you a lower bound for some kind of functions like majority, correlation, and those kind of problems. So, like even for functions, given that you have a Fourier growth bound for all functions, it doesn't really allow you to prove a lifting theorem for functions other than majority and correlation. So, if you want to lift relational problems, first of all, I guess the problem should be something for which Fourier analytic techniques are useful. So maybe for specific relational problems that, look like kind of like majority or something like that. So maybe if there was a more explicit example of an interesting relational problem, maybe maybe it's possible to lift it using Fourier growth. But yeah, I think the biggest hurdle in going from Fourier growth to lifting theorems is that Fourier growth only gives you a lower bound for a few interesting family of functions. And as such, I don't know how to use Fourier growth to prove lower bounds for an arbitrary function. So that's somewhat the difficulty in going from Fourier growth to lifting theorems.
I see. Okay, so then I suggest if there are no further questions, we maybe have a break. So we're back after the break, and the plan is now to listen to some more of the technical parts. So over to you, Uma.
Thanks. Okay, yeah, let me start by just recapping what we're trying to do. We're studying this quantity called level L mass, which is the sum of absolute values of size L Fourier coefficients. This has some motivations in learning theory, pseudorandom generators, and quantum versus classical separations. We're going to be interested in bounding the level 1 mass of XOR fibers of communication protocols. So XOR fibers come up naturally in the context of XOR lifting. And the definition is as follows. You take a communication protocol, fix a particular Z, and look at all inputs X, Y, whose XOR is Z, and take the average output of the protocol over such inputs. This is a function of Z and is called the XOR fiber. In this talk, we will prove a Fourier growth bound on the XOR fibers of cost D protocols. In this talk, I will just show the level 1 bound, some ideas behind the level 1 bound, and it turns out that the level 1 bound is order square root D, and this is optimal. The level 2 bound we are able to show is square root D cube. And as a result of this, we had some applications to new proofs of the gap Hamming lower bound, new proofs of Fourier growth for decision trees and parity decision trees, as well as improved quantum versus classical separations. So let's recap the proof overview. Yeah, so there were 3 parts to this. In the first part, I'm going to express the level 1 Fourier growth as a martingale. This martingale will turn out to have some nice geometric interpretations. So I'll just describe that very briefly now. So first, so this is the first step, and the second step is going to be about showing how to use two-wise independence to prove bounds of the Fourier growth. Step 3 I already hinted at before, so I'm not going to go into it too much. So for now, I'm going to describe step 1 and step 2. And step 1 is where I'm going to describe the Fourier growth as a martingale. And this martingale has some geometric interpretation, which let me describe now before going into the details. So you can view a communication protocol as a random partitioning process of the input space. So you have the space, initially you have the space of all possible Alice's and Bob's inputs. And as you go down the communication protocol, you are partitioning these sets recursively. Now, if you're sampling the inputs of Alice and Bob uniformly and independently, this induces some kind of random partitioning process of the input space. Furthermore, if you keep track of Alice's and Bob's centers, that is, you take Alice's and Bob's sets and compute the geometric centers of these sets, the inner product between these 2 centers captures the level 1 Fourier growth of the XOR fiber. In more detail, you can upper bound the level 1 Fourier growth by the expected magnitude of the inner product between Alice's center and Bob's center at a random leaf. This is what I'm going to describe in more detail in step 1. So let's get into the details. So first, as I described earlier, you can view the communication protocol as this binary tree, which informs the players what they need to do at each step. Given any input X, Y, it is going to reach some leaf of this tree, and the label of the leaf is declared as the output of the protocol. Throughout this talk, we're going to sample the inputs of Alice and Bob uniformly and independently. This is going to induce a random walk down this tree. In particular, you're going to get a random leaf of the tree. Now, if you look at any node of this protocol, and you look at the set of all inputs X, Y that reach this node, it is a rectangle, A times B. So for every node of a communication protocol, the set of all inputs reaching this node is a rectangle A times B. When Alice speaks, she's announcing f of x for some f, and this effectively partitions A into two parts. Those points for which f of x is 1 and those points for which f of x is minus 1. So when Alice speaks, she effectively partitions her set A, and when Bob speaks, he partitions his set B. Therefore, you can view the communication protocol as a process of recursively partitioning the space of inputs of Alice and Bob. Now we're ready to describe the Fourier growth as a martingale with respect to this random partitioning process. The idea is to keep track of the centers of Alice's and Bob's sets throughout the protocol. So just to recap what I mean by center, this is just the geometric center of a set, also called the center of mass, centroid, and so on. The center of a set is defined to be the expectation of a random point sampled from the set. So this is an n-dimensional vector. And in terms of Fourier coefficients, this has a very nice interpretation. The center of a set is essentially the list of the level 1 Fourier coefficients. There is some normalization here. You need to take the normalized indicator functions. But morally, the center of a set is captured by the list of the level 1 Fourier coefficients, and it really corresponds to the geometric center or center of mass. Now, we keep track of the centers of Alice's and Bob's sets as we go down this protocol. So we use U to denote the center of Alice's sets and V to denote the center of Bob's sets. First of all, U and V are themselves vector-valued martingales. When you take a set and you partition it into two parts, the average center of mass of the two parts equals the center of mass of the original part. Therefore, these center of masses of Alice's and Bob's sets are individually vector-valued martingales. We're going to be interested in the inner product between Alice's center and Bob's center. I claim that this is a real-valued martingale. The reason is that when Alice speaks, only her center of mass changes. And when Bob speaks, only his center of mass changes. As a result, the inner product between Alice's and Bob's center is also a martingale. Now, the main claim is that this martingale has close connections with the level 1 Fourier growth. In particular, the level 1 Fourier growth of the XOR fiber is at most the expected modulus of this martingale at a random leaf. So in the next few slides, I'll try to give some intuition as to why this is true. But are there any questions about the setup at this point?
I guess one naive question is like the martingale. I mean, it's a random process. So what is the randomness here?
So the randomness is coming from X and Y being sampled at random. So there is a certain probability of going to the right and left. So in other words, you're partitioning a set into two parts, and you're picking one of the parts at random with probability proportional to the measure of the part.
Okay.
Yeah.
Okay, got it.
Yeah. Okay. So in the next two slides, I'll try to give the intuition behind why the level 1 Fourier growth has connections to this martingale. So here is what we want to show. We want to show that the level 1 growth is at most the expected modulus of the inner product between Alice's center and Bob's center at a random leaf. So let me first describe a very high-level proof of this. And the proof is as follows. First, let's just look at a single rectangle, A times B. I claim that if you look at the level 1 growth of the XOR fiber of just a rectangle, it is the inner product between the center of Alice's set and the center of Bob's set. Once you have this, the main claim essentially follows by adding up over all the rectangles. There's some normalization, but it all works out. So once you can understand the Fourier growth of the XOR fiber of a rectangle, you can understand the Fourier growth of XOR fiber of a communication protocol. So for now, let's just focus on rectangles. So the idea is as follows. First, if you look at a rectangle, the XOR fiber is basically the convolution of the two sides. Secondly, if you look at the Fourier coefficients of a convolution of two functions, it's the product of Fourier coefficients. Finally, if you look at the center of a set, it is captured by the list of level 1 Fourier coefficients. So, in other words, the level 1 Fourier growth of the XOR fiber of a rectangle is basically the summation of A star B hat I over all I, which turns out to be summation A hat I times B hat I, which by this relation is just the inner product between the center of A and center of B. So this is a very high level explanation of what is happening here. But if people are interested, I can write down this explicitly, and maybe let me just have this slide which actually explicitly proves this, without using convolutions. Yeah, okay, so since it's just one slide, maybe let's just go over it.
So, but okay, yes, because I was going to
Yeah.
say, so basically you're saying this is like this slide, if I just know the definitions and do the calculations carefully, then this will sort of take me from the top of the slide to the bottom of the slide. That's what you're saying. Or is
Yeah,
there like
yeah.
anything exciting happening or anything non-obvious, or it's more like a carefully unpacking?
Yeah, if you're willing to believe that, then okay, yeah, we can continue. Yeah. It's basically a careful unpacking. But yeah, I guess the main steps are kind of that if you look at the
I mean, please feel free to do the main steps. So that's
Oh.
I didn't intend to fast forward or anything. I'm just trying to understand sort of, yeah.
Yeah, basically you can, I mean, it's just one page of just following the calculations, but yeah, at a very high level, I would say that for a rectangle, the XOR fiber is just the convolution of the two sides. And you can write down the Fourier coefficients of a convolution, it's the product of Fourier coefficients. And yeah, I'm not sure whether we should, okay, let's just do it. Yeah, so in this slide, I'm going to explicitly show that the Fourier growth is at most the expected modulus of the inner product between the centers. So let's just see the proof. Okay, so first I'm going to write down what the Fourier growth is. And for now, let's just forget about the signs. So let's just take summation H hat I. And by definition is just this quantity. This is the definition of a Fourier coefficient. And now I am going to replace H by the definition of an XOR fiber. So what is H of Z? It's the expectation of C of XY conditioned on X XOR Y equals Z. Now under this conditioning, Zi precisely equals Xi times Yi. And therefore you can rewrite this expression as this. And now you have an expectation over Z followed by an expectation over X and Y. So you might as well ignore this expectation and write expectation over just X and Y. So basically to go from here to here, it follows by writing down what an XOR fiber is. And now I'm going to write the protocol as a sum of rectangles. So here I have expectation because there's some normalization going on. But basically the output of a protocol is the sum over rectangles of the indicator function of the rectangle times the output of the protocol on that rectangle. And now I'm going to use, so in this step, I'm just swapping the expectations. And here I'm going to use the property of a rectangle that A times B of X comma Y is A of X times B of Y. And now you have A of X times Xi and B of Y times Yi, which again, by the definition of Fourier coefficients, since you're taking the expectation, is A hat I times B hat I. Now, when you sum A hat I times B hat I over all I, you basically get the inner product between the center of A and the center of B. Finally, I'm going to use the fact that C of AB, the output of the protocol is, plus minus 1. And therefore, you can bound this product by the modulus. Okay, so this is a very, very quick proof of this connection between the level 1 Fourier growth and the inner product between the centers. Right, so now that I've given this connection, I'm just going to restate the entire problem about Fourier growth geometrically. So even if you didn't follow the definition of Fourier coefficients, now is a good time to jump back. I'm just going to restate the level 1 bound completely geometrically. And the interpretation is as follows. We have a random partitioning process of the input space of Alice and Bob. Initially, Alice starts by partitioning her set into 2 arbitrary parts and chooses a part at random with probability proportional to its measure. Based on this, Bob partitions his set into 2 parts and chooses a part at random with probability proportional to its measure. Alice does this again. Again, Bob partitions his set, and so on. They do this d times. This partitioning process can be adaptive in the sense that the way the players partition the set can depend on the history up to this point. We keep track of the centers of Alice's sets and Bob's sets, call them U and B. And our goal is to control the inner product between U and B. We want to show that the expected modulus of the inner product between Alice's final center and Bob's final center is at most square root d. So this is a geometric restatement of the level 1 bound. So yeah, this is what we want to show. So looking ahead, it will turn out that each of these vectors, U and V, that is the centers of Alice's and Bob's sets, each of these vectors could individually be square root d long. So a priori, their inner product could be as large as d. But what we want to show is that even though each of these vectors could be square root d long, they're going to be typically orthogonal. That is, their inner product, which could be d in the worst case, is typically only square root d. So in the next slide, I'll describe this bound in more detail, but are there any questions up to this point about the setup?
I have a question.
Yeah.
So going back to the previous slide, what would be the correct analog for a higher monomials previous slide? The calculation.
That's a great question.
These tautologies.
Yeah, that's a great question. So what ends up happening here is you have some kind of level 2 center of mass. So earlier we defined the center of a set as basically the expectation of Z, but now you look at expectation of Z tensor Z, which will give you the list of level 2 Fourier coefficients.
And that means in particular for this step, it's independent of the degree you're considering about, which means there is a natural analog in higher degree as well, just to that.
Yes.
Either the partition is going to large or some later steps would be more adversarial to higher degree.
Okay. So yeah, the thing we want to bound will turn out to be some kind of inner product between the level 2 center of mass of A and level 2 center of mass of B. And to do this, you need to ensure 4-wise independence. And that is what we're not able to do. We're able to clean up sets to ensure 2-wise independence, but when you try to clean up 4-wise independence, then you end up having too many steps, basically. Yeah, sorry, does that answer your question?
Yes, of course. Thank you.
Okay. Yeah. So any other questions about this picture? Okay. So yeah, let me describe the worst case bound of order D.
Actually, yeah, so one question. I was thinking about, sorry, getting back to this deterministic versus randomized, because here you usually get like problems with somehow, I don't know, rectangles not being monochromatic or anything. But here somehow the reason why this works is we could think of, in this setting, we're perfectly fine with Alice and Bob just as a first random step, they just sample a deterministic protocol that they're going to use for this particular input. And it's sort of all the calculations that you do and all the expectations will sort
Yes.
of just by linearity over this choice, sort of. I just need to, as long as I do the calculations for deterministic protocols, then the transition to randomized is somehow more or less for free.
Yeah, exactly. That's what I feel with generally Fourier analytic things, because yeah, Fourier coefficients are just, each Fourier coefficient is just a linear convex combination of the Fourier coefficients, the deterministic protocol that you pick. So
Okay.
Yeah. Yeah, okay. So okay, yeah. So for now I'll show that this inner product can be at most order D. And this was done by an earlier work with Ran, Raz, and Avishai et al. So you can show that at a leaf, the inner product between the centers is at most order D. And the reason is that each of the centers themselves are square root D at most in norm. So this follows by an application of the level 1 inequality. The idea is that since A and B, Alice's and Bob's sets, are not too small at a leaf, their centers cannot be too far from the origin. This is what the level 1 inequality says. It says that if you have a set that is not too small, its center cannot be too far from the origin. In particular, if your measure is 2 to the minus d, the center is at most square root d away from the origin. So this implies that Alice's and Bob's centers, U and V, are at most square root d long, and therefore their inner product is at most order d. What we want to show is that typically, not only are U and V small, their inner product is much smaller, in the sense that they're roughly orthogonal. So we'll show that the expected square of the martingale is also at most order d. By Cauchy-Schwarz, it would imply that the expected modulus of the martingale is at most square root d, which is what we want.
Well, somehow you're saying Cauchy-Schwarz is like badly off because it admits that maybe they're fairly like parallel, and you're saying no, they're
Exactly.
nowhere close.
Exactly. So I think in the next slide I have an example, a visual example of this, which shows that although U and V might be large, typically they're going to be orthogonal. So let's look at an example that shows this. And this example is just a very simple example. It's just a decision tree where Alice and Bob reveal the first t coordinates. This effectively partitions the input space into subcubes corresponding to the values of the first t coordinates. Now, if you take a worst case path, in the sense if Alice and Bob both set their first d coordinates to be 1, then the subcubes you obtain are A and B, where you set the first d coordinates to be 1 and the rest of the coordinates are free. This is the leaf that you reach on this input. And now if you look at the centers U and V, it's going to be exactly this vector, where the first d coordinates are 1 and the rest are 0. In this case, the inner product between U and V is actually going to be D. So this shows that the worst case bound that we derived earlier is tight, because there are leaves where U and V will be perfectly parallel, in which case the inner product could be D. But if you take a typical leaf, the situation is going to be different. The reason is that for a typical leaf, the values you set to Alice's coordinates and Bob's coordinates are going to be independent, because you sampled the inputs of Alice and Bob to be uniform and independent. In particular, if you look at the centers of Alice's and Bob's sets, they're going to be described by these vectors A and B that are plus minus 1, D length vectors of plus minus 1 entries, and they're independent. Now, if you look at the inner product between the centers U and V, it's going to be the inner product between A and B, which is just a sum of D random plus minus 1 random variables, which is typically square root D. So this says that on a random leaf, U and V are going to be roughly orthogonal. This really highlights the phenomenon of cancellations that happen when you take a random path. What we want to show is that no matter what kind of communication the players engage in, there's always going to be this kind of cancellation phenomenon. So this is what we want to show. Are there any questions?
I think the intuition is very strong, but how to prove it is another matter, right?
Yeah, the difficulty is that these sets can be arbitrarily partitioned, and this partitioning process also can be adaptive, the way they choose their sets.
Right.
Yeah. Yeah, that's kind of the difficulty. Okay, so maybe in the next 15 minutes or so, I'd like to give some idea on how to do this. How do you control the martingale? And the main focus is going to be to use this spectral two-wise independence and show why it's so useful. For now, maybe let me start by working backwards. Let's try to control the martingale and see what we need. Okay, so here is the martingale that we care about. It's the inner product between Alice's and Bob's center. We want to show that the sum of squares of step sizes of this martingale is at most order D. So let's compute the step size, and let's assume that for now Alice is speaking. Then only her center changes. Let's call ui plus 1 the change in Alice's center. Then you can write down that the step size equals this ui plus 1 times vi. It's the inner product between the change in Alice's center and, oh, I'm sorry, this should be Bob's center. Actually, let me just fix that. Sorry. So there's no confusion. Yeah, this is Bob's current center at time I.
Yes.
So this is the step size, yeah. So let's try to control it. Yeah, there might be some typos in the next slides, but please bear with me. Yeah, so let's assume for now that ui plus 1 has norm at most 1. So let's imagine that Alice at each point is just adding a unit vector to her center of mass. In this case, you can bound the step size by the norm of Bob's center. Again, this is not change in Bob's center, this is just Bob's center. And what bound does that give us? I claim that that still does not give us the right bound. So what you get is the square of the step size is at most the norm square of Bob's current center, which we saw could be as large as I. After I steps, Bob's center could be square root I from the origin, and this is tight by the decision tree example. And when you add this over all steps, you would get D square as opposed to D. So just using Cauchy-Schwarz for each step is not enough. And what we're going to show is that the step size square is at most the change in Bob's center in the previous round. We're going to use spectral two-wise independence to show this. So as such, this might look a little counterintuitive. So at step size, the step size at time I can be expressed in terms of the change in Alice's center at time I, but we're going to bound it by the change in Bob's center at time I minus 1, essentially. Basically, we replaced the norm of Bob's current center by the norm of the change in the Bob's center. So by the assumption, this quantity is at most order 1. So the step size at time I becomes order 1, and therefore, when you add this up over all steps, you get order D. So this is what we're going to show. Yeah, so now let me talk about spectral two-wise independence before saying how we show this. So I already hinted at this before, but spectral two-wise independence is as follows. We say that a set is elongated in direction V if the variance of the set in direction V is large. We say that a set is spectrally two-wise independent if it is not elongated in any direction. In other words, if you sample a random point from S and you look at the covariance matrix, this covariance matrix has bounded spectral norm. We want Alice's and Bob's sets to satisfy this property throughout the protocol. So this is the definition of spectral two-wise independence. Now I'll justify why this helps us bound the level 1 Fourier growth. And to do this, I'll need to talk about a slightly unusual step called the Gram-Schmidt step. Imagine for now that Alice executes the following communication step. Imagine that she reveals the inner product of her input with Bob's current center. So Alice is announcing X dot V, where V is Bob's current center. What this does is it takes her set and it partitions her set into slices along the direction V, or perpendicular to the direction V. So this is what we call the Gram-Schmidt step. And first of all, this step might throw up a lot of red flags. It's a real communication. So how do we handle this kind of real communication? And as I hinted at before, there are two choices. We could tell Alice to announce this real number up to some precision. This would make the communication Boolean. But this truncation seems to introduce some errors, and it does not give you the optimal level 1 bound. You lose some polylog factors. If you want the optimal bound, you really need to allow Alice to communicate a real number. But this forces you to allow Alice's inputs to also be real. Because if X was a Boolean vector, by revealing X dot V as a real number, you could end up revealing X. So if you allow real inputs, if you allow real outputs, you also need to allow real inputs. For our level 1 bound, this is actually what we do. We sample X and Y from the standard multivariate Gaussian. So now it's a continuous space. And we also allow the protocol to communicate real numbers.
Can you say anything about, I mean, communicating a real number is sort of allowing Alice a priori to send infinite amounts of information, right? Is there some way to make sure that Alice doesn't cheat?
So yeah, if you had only Boolean inputs, then indeed this is cheating. But if you had real inputs, it's not so much cheating because you're just cutting down the dimension of the space by 1. There is still infinite amount of freedom within the slice.
Okay.
Yeah. Yeah, this is a somewhat peculiar part of our proof, but it turns out to be like really crucial to give you the optimal level 1 bound. And maybe it's not so surprising because the earlier gap hamming proofs also really required sampling real inputs. So yeah, for some reason to get the optimal bound, we really need to allow real inputs and real outputs. Yeah. But for this talk, you can keep either picture in mind. And if you don't mind just log and loss and parameters, you can just imagine that they reveal it up to some precision and everything else works out.
I mean, I guess in particular for higher dimensions, it's only, wait, how much is log n compared to like the other things we're...
It's small, yeah. So this is what we do for higher levels because we don't care about the optimal dependence. I mean, we care about the dependence on D more than other things. So for higher levels, we actually do this.
Okay.
Because it's a little simpler to think about, I guess. Yeah. Okay. So this is the Gram-Schmidt step. And what's so nice about the Gram-Schmidt step is that it expresses the change in the martingale in terms of the elongatedness of Alice's set. So the Gram-Schmidt step is what connects the change in the martingale with the elongatedness of a set. In more detail, if you compute the change in the martingale during the Gram-Schmidt step, it is precisely equal to the variance of Alice's set in the direction of Bob's center. So let's look at this. It's not so hard to prove. So let's compute the step size square of the martingale as a result of the Gram-Schmidt step. By definition, the change in the step size square of the martingale is basically the expected square of the martingale at time I plus 1 minus the square of the martingale at time I. This is the value of the martingale at time I plus 1, and this is the value of the martingale at time I. So the first line just follows by the definition of the step size square. Now, for the second line, I'm going to replace ui plus 1, u at most I plus 1, by the definition. So recall that ui plus 1 is the center of ai plus 1. So you can replace u by the expectation of x, where x is sampled from ai plus 1. So this here is just by definition of the center. And similarly here, you can replace u at most I by the expectation of x, where x is sampled from ai. So the second line here is just by definition of the centers of the sets. And now here comes the key part. So here I claim that you can pull the square from outside to inside. The reason is that any point within a slice ai plus 1, all points have the same inner product with this vector v. So all points in this slice have the same inner product with the vector v. As a result, this expectation of x dot v is actually expectation of a constant that depends only on the slice. So you can pull the square from outside to inside. And now this quantity here is precisely how elongated Alice's set is in direction v. It's basically the variance of x dot v. So again, the calculations are not so important, but what's important here is that during the Gram-Schmidt step, the change in the martingale precisely equals how elongated Alice's set is in the direction of Bob's current center. This is what makes the Gram-Schmidt step so useful. And of course, arbitrary protocols will not have this step, but we will introduce this step. So given an arbitrary communication protocol, we'll first insist that the players do this Gram-Schmidt step. So at phase I, before Alice communicates anything, she first starts by doing the Gram-Schmidt step. She announces the inner product of x with v, where v is Bob's current center. And then she proceeds to do whatever she was supposed to do. Then when Bob is supposed to speak, he similarly starts by announcing the inner product with Alice's center, and then does whatever he was supposed to do. So this effectively doubles the cost of the protocol. And what is the advantage of this? Well, we saw from the previous slide that the change in the martingale during the Gram-Schmidt step equals the variance of Alice's set in the direction of Bob's current center. But now I claim that the variance of Alice's set in the direction of Bob's center actually equals the variance along the direction vi, which is the change in Bob's center. The reason for this is that Alice in the previous phase has revealed the inner product with Bob's previous center. As a result, in this phase, any change in Alice's center is orthogonal to Bob's old center. In particular, if you look at the set AI, at this point, since Alice has already revealed the inner product with Bob's old center, the variance along Bob's old center is going to be 0. So when you're computing this variance of AI in the direction v at most I, you might as well subtract v I minus 2, which is Bob's old center. And what you get is essentially vi, which is the change in Bob's center in the previous phase. Okay, so basically using this Gram-Schmidt step, you can express the change in the martingale during the Gram-Schmidt step in terms of the quantity that we cared about, which is the variance along the direction of the change in Bob's center. And now by 2i's independence, you can show that it is at most norm of vi squared. Okay, so this is how 2i's independence allows us to bound the change in the martingale using this quantity norm of vi squared. What about the other steps? Well, another advantage of the Gram-Schmidt step is that the martingale does not change at all in the other steps. Any change in Alice's center during this step is going to be orthogonal to Bob's current center, because at this point, she already fixed the inner product with Bob's current center. So any further change to her center of mass is going to be orthogonal to v at most I. Therefore, the martingale does not change in any of the non-Gram-Schmidt steps. Okay, so to summarize what happened here, we introduced this step called Gram-Schmidt step. One advantage of this Gram-Schmidt step is that the martingale only changes during the Gram-Schmidt steps and not during the other steps. Furthermore, the change in the martingale during the Gram-Schmidt step is precisely equal to the variance of Alice's set in the direction of vi, which by 2i's independence is at most norm vi squared. So this is how spectral 2i's independence allows you to bound the Fourier growth, in particular bound the sum of squares of step sizes. So this is all that I wanted to say regarding step 2. Yeah, I did not have much to add regarding step 3 other than what I already said before. So I'm happy to stop at this point and take any questions.
Yeah, I have one question.
Yes.
So it's very interesting concept of this I call it spectral toolwise independence. Should it be called, should it be better called a uniformity requirement than independence?
I guess you could say that.
So for example, if all the points are centered around very closely some one point, then this is perfectly spectral toolwise independent or even higher wise independent if you like, I think.
Mhm.
So in particular, there are established uniformity measure of functions if you view those points as indicator functions on the Boolean cube. Would that be useful, or you would imagine it to be useful?
Actually, I'm not sure I follow in what sense it is. I
Mm,
mean,
okay,
there is some,
just-
yeah, there is some kind of like these vectors are an isotropic position, which is, I guess that's another way to view it, but I'm not sure I understand the uniform picture actually.
Okay, then the question is why why the word independence appear here?
Okay, so okay, so well, okay. So the first thing we try to do is we try to say, okay, what is the obvious notion of, so for decision trees and parity decision trees, you can use perfect independence. So now the question becomes, what is the approximate notion of independence that you could use? And one thing you could say was, you could look at expectation of xi xj minus expectation of xi times expectation of xj and require that to be small. So that's almost two-wise independence, but that is not enough. We need something stronger, which is that this covariance matrix, if you look at expectation of XX transpose minus expectation of X transpose, this has small norm. So this implies in particular that every pair of coordinates is almost two-wise independent. So if the covariance matrix was exactly 0, then it's perfect, then it's the same as two-wise independent. But now we're saying that the covariance matrix has small spectral norm, which in particular implies that the pairwise correlations are small. So that's the sense in which we think of this as pairwise independence. It's almost pairwise independent.
Okay, just to dig slightly in, or to ask more question about this. By two-wise independent, you mean actually, if I pick 2 points from the set of L from S,
Mhm.
the covariance of them is almost sorry, the variance of the, or you this is
No,
a
I'm just
question.
picking one
Yeah.
point. Yeah. Yeah,
You
it's
mean
not.
coordinates or pairs of
Yeah, coordinates. Yeah.
coordinates? Okay.
Yeah. The coordinates are pairwise independent. That's right. It's not the points. I mean, yeah, it's not like you're picking 2 points from S, but rather you're looking at xi and xj. And xi and xj are pairwise independent. That's what I meant.
Okay.
Okay, any other questions? Before we thank our speaker again for an amazing tour of this paper. I mean, it's really, really nice. And especially like somehow, yeah, providing the intuition along the way. But so what do you think? I mean, pushing onwards to like higher dimensions, is it somehow you want a higher spectral independence and then somehow be able to do the calculations and control it? Or like, do you think you need to do something completely different or?
Yeah, I feel like this is very intuitive. This is just a very geometric question. You have a set and you want to partition it into parts that look kind of four-wise independent. I feel that it should be true, but I just don't know how to prove it. So I would think that if there should be a proof of this. Yeah. It's just that coming up with the right potential function and things like that, kind of hard. But yeah, I would think that it should work, but yeah.
Okay, fair enough. And thank you so much again for this seminar. So
Thank you for having
again,
me.
thank you.
Nice talk.
Thanks.